when you think about it, our computers now are capable of doing multiple tasks simultaneously, and that is sort of a shift from days of old DOS, where you had one prompt and you had one process running, one program running and executing in that environment. And with Unix, they branched out and developed the idea of a process or threading, where you can have one process capable of running at one time and then another process waiting to gain execution time, or time to run and time to do its process, time to do its job. And that's basically what I'm going to discuss. First of all, what is process? And there's several things that define what a process is. Every process has a body of code to execute, meaning that it's given a specific job, and that job is the only thing it's going to do. It has a reserved piece of memory, meaning that it's been allocated so much memory. Maybe it might be allocated more memory, but it has its own reserved place where it can, write data to or read data from. So it can execute the code, and it can store bits of information that it needs in locations in the memory. It has its own set of file descriptors, which is sort of detailed, but it means that it can open up files, and it can close files, and it has its own sort of environment separate from that the OS provides it, and it allows it to gain access to other areas of the system. And it has a unique process ID. And I think some people here, obviously, who've been exposed more to Unix systems, and they've been in environments where you have a runaway process or something. What do? Your computer is using 99% of your resources. What are you going to your processing time? So you have to go kill it. So you might drop out here, and you might go and look at top, and you can see here that you have your process ID, and this is the one you don't want to kill, obviously. It'll bring down your whole computer. And they're listed out here, different process IDs, and each one of these is a separate running process. It could be an entire program, or it could be a process running within a program. And when you have a program running, it is considered a parent process, and it can fork off these children, and these child processes sort of report back to the parent process, and they have a little bit of a communication going between them. And that's kind of what I want to talk about, is communication. It might be on a single program level, it could be on a program-to-program level, and it could be a program running on one machine communicating to a program on an entirely different machine. So all of those are sort of related. That's inter-process communication. And get out of here and go back to the slideshow. Okay. And how do they communicate? And there's several different ways that they can do this. Some of these listed right here, they're fairly detailed, and they're really used only in a programming environment where you need to pay a lot of attention to what you're doing. Well, you always have to pay a lot of attention to what you're doing, but you have to be very careful, because these can cause very disastrous results sometimes, depending on the priority or what type of user is running the process. If it's a root using process, it can do some serious damage. These are the ones that I'll discuss today. These are the more commonly used ones that you interact with on a daily basis that you probably are aware of. These you probably are not as aware of, and I'll talk a little bit about them. First is shared memory. And like I said, every process has its own memory that it's associated with. But they can also share memory, which means it's pretty dangerous, but it means that one process can read and write to this block of memory, and another process can read and write to this block of memory. So they both are accessing this area. And they might put something there, and another process might read from it or take from it or do something. It can be very disastrous if you're overwriting certain areas of RAM that it shouldn't be and doing things. So Unix has various structures that keep those shared memory areas secure, and they keep them from destroying each other. Signals are another way of communication, and I bet you've probably seen this, like when you had a disaster, like your program crashed, and it's, it might say, seg-v or something like that, or it gives you some signal, comes back, or it just prints out a little error code or something like that. Most of the time, these are signals that they're interrupts. Like something happens, like you can send a Control-C as an interrupt where you kill off a process that's running. That's sig kill. So that's another way that process can communicate. There's message queues, which one process kind of mediates and sends these messages to other processes. So one is kind of like a master process, and it serves signals and things to other processes. That's another form. And semaphores, which are pretty close to what a semaphore is in the real world. A semaphore was used, used in France originally, but then later on used on a smaller scale for trains. And so when a train had permission to drive through this area, it would have to look at the semaphore, which would be like a flag, sort of like a flag, that arm that came out. And if they had the ability to move past the area, they had a flag and they can go. If the flag was down, they would stop and wait for the other trains to go by. So this is mainly used by OSs, the operating system, to say you have read access and you have write access, kind of like mediate. So semaphores are a way of doing that. And these are like pretty low level. These are some things that you probably will not like, unless you're really like interested in programming, you're probably not going to deal with these very much. The ones I'll talk about today are pipes, which if you've ever seen a pipe in action, you probably have if you've ever dealt with the command line. But you also deal with them on a daily basis, and what they are is a one-way stream of information sent between two programs. So a program can open up a pipe to another program and send data to it, and it's a one-way transmission. And all it really assures is that the memory sent in this order comes out in that order on the other side. And then there's also a FIFO, and a FIFO is a named pipe. And you also have seen these, because if you've ever happened to get curious and look at your devices in the /dev folder, you see you have urandom. We were just talking about that one earlier. It's a FIFO, which means like first in, first out, like a buffer. And that's how you're going to access your CD-ROM drives. That's how you're going to access your hard drives. It buffers in and out through. And you can actually make these with a make node. And I'll show you how to do that a little bit later. Sockets are a big one. And that's where it's point-to-point, two-way communication. And it can be done locally on your system, which is done fairly commonly. And it's also done obviously like through foreign access, and that's called INET, or internet. Your internet protocols are using sockets. So a socket is basically what you think of it. It's an endpoint, like the socket you have like for a plug, a socket plug, right? And programmers like come up with easy names that you can kind of associate with the real world, like semaphores and FIFOs, sockets. So it should be fairly simple, and we'll go into like more detail on these. I'll talk about pipes a little bit. Historically, pipes were like the main way that communication was done. Sockets were sort of a newer thing, and that was actually came out of BSD, or the Berkeley School, Berkeley Software Department came up with like their idea of what a socket should be. But before that, they only had pipes. Nowadays, pipes are done with sockets, and that's, I think I mentioned that right here. Modern implementations use sockets as the basis for pipes, because sockets are so good, they just, why not use them for pipes too, So what they are is a one-way byte stream between related processes, and usually there's a parent-child interaction. And I'll give you like it's not going to be super visual, but I'll try and make this.
Can you blow up the font like really big on that? Do you have that ability?
I would have to go and edit my XDefaults. Let's see.
Oh, okay. No.
Well, I could do it like this. So here's a list of, I'll list user bin, right? This is going to be my bin file. It's got a ton, I've got a ton of applications in there. This is like the simplest way I can show a pipe. So I've got a ton of applications in here. And if I really would like to show all of them, you know, obviously I can pipe it to less. And what I'm writing here, if I could, is there a pen that I could use to write on the board real fast?
That one that I used, it was, I think it's in front of the bin there, on the table.
All right. You need the logo? Please, please. That's okay. Since it's a small type, I'll write it up on the board. So I'm typing ls, which is going to list the contents of the directory. But you can see the contents of this directory are fairly large. So what I'd like to do is I'd like to list this directory, but I'd like to view it. And there's a good program for viewing material coming in from what's called the standard input. And this would be a case of the standard input. So LESS is that program. So what I'm going to do is I'm going to type ls, which is going to list, and then I'm going to pipe it. I'm going to use this pipe character. In bash, it's just a bar. And then I'm going to send it to less. So ls is the parent process, and this pipe is going to make a child process of less. This is going to be the child. And then it's going to send a stream, a one-way stream of data to less. And I'll show you what this will kind of look like here. I mean, everyone's pretty much seen this, but it's a good example. So before, you saw there were 4 rows of text, but now you see that we have text here, and it's in less. And this is a child process, and I can, you know, use the capabilities of less. There's like an entire, I think there's like an editor. Okay, I can't edit the standard input, but less has like tons of features. And so what this has done is ls has created a child process less, sent the information, and I can use it like normal. And that is the fundamental easiest way to show pipe. And you might use this fairly often. If you don't, there's programs that you're using that are using pipes and doing that too. If you were to program a pipe in C, you can use, there's a function called pipe, and in here you're going to create a pipe, and you give it a name and things like that. It's rather complex, and won't go into it. I'll talk a little bit of programming at the end, and I can show you. I'll show you more about sockets and pipes. But back to the presentation. Enough of the tangents. I hope that wasn't confusing. Is there any questions about that sort of? Or? Okay, that is pretty basic. Okay, the system also assures that the order of output is the same as the order of input, right? So what is first in is going to be what's first out, and that no data is lost in the communication. So it's really a reliable way of communicating. If it does break in communication, a signal is raised, and that signal is communicated through what's called an error value, like an error code, basically. And it is programmed with the C function pipe, and it can be found in this library of data. You know, that's for C implementations. Every language has their own way of doing it. Perl has their own. You know, I think it's io it might be io.pipe. I'm not sure exactly. I haven't really actually made sense.
There's a function standard in. You can use that. This is a way to process data for each standard in.
Oh, okay, right.
That's kind of a pipe type.
Yeah, it's similar because what standard in is, it's very much like a pipe because it's a byte stream. It's a stream of information, and what that is it's not actually a stream. It's more of a grouping of data, and it reads that grouping of data so reliably and so fast that it's like a stream. You know, you can think about like a river is a bunch of particles of water, but they move so rapidly and so together that you consider it one whole unit. And so that's the way pipes kind of communicate. And like I said, pipes are based on sockets. And really what I'd like to get into is talking a bit about sockets. And of course, they're called BSD sockets because they were first implemented in the Berkeley software department. Before that, like I said, they had this very interesting sort of protocol, like System 5 was an old version of Unix. And they had their own way of transporting information. It wasn't very reliable, it was very hard to do, and so the students there, I guess, at the university, the several professors, in fact, I think his name was Peterson, the guy who developed Unix originally at Bell Labs, was a professor at Berkeley Berkeley University for a while. So he brought that back and they developed it there. What it does, or what sockets do, is they allow point-to-point two-way communication, like I said before. They serve as the endpoints. And the endpoints have an IP address bound to them, meaning that these endpoints are addressable. So if one process sends data from one area, it knows the address of the other end, and it can make it over there successfully. They also have a type. All sockets have a type, and they're selected when they're created. And there's also options that you can give to sockets. And those options can affect the way the information is transmitted. It can affect how long the socket stays open. I'm sure some people have had instances where they try to they open up their web browser and they typed in an email, or not email address, a URL that wasn't there, or their server's down, and then you sit there and you wait and you watch the spinning icon or whatever, you're waiting for the web page to resolve, and it never does. Well, one of the options there selects how long it waits before it times out. And that is one aspect of sockets. They also exist in domains, or areas that they govern. If you're dealing with a local domain, you might be dealing with Unix, and that would be on your own computer. If you're dealing with internet, it's within the internet domain, meaning that it's outside of your system. And there's also there's the NS domain, which is what the Palo Alto Research, they came up with that. That was, it's what the Ethernet was originally written with. But there's 23 different domains that you can use, and they're listed under socket.h, which is a header file for C. Obviously, like I said before, every language has their own way of doing that. They're originally created not bound to any address. So your socket originally is a very kind of abstract thing. In fact, it's just a number. And then it's bound to an address, and more bits of data are bound up and collected, and then now you have a socket. You kind of have to build it up a little bit by binding it to a name. And also, lastly, I'll talk about just the general information is that sockets are not, their communication is asymmetrical, meaning that it's not information being sent here and information being sent here immediately. There has to be a client-server relationship between these two, and that's the main reason why you think about web pages and things are, you think about servers, and you think about you have your client program. If you're dealing with a chat client or something like that, your IRC chat client, and there's also IRC servers, and everything that you use or communicate with obviously has to have some sort of master process, which is waiting, and some sort of child process, or, well, they're not exactly child-parent, but it's more of server-client. And that's a very appropriate term to use, because this is waiting to serve, and this is asking for information or giving information. It's like I said, it's two-way communication, so both of these will be sending information back and forth. But initially, the server will sit there and wait until it receives some sort of connection to initiate that communication. I'll talk a little bit about the types. There's 4 major types. Obviously, there can be endless types, whatever people create, but it just seems like these 4 are the ones that you really need. In fact, you only really need the top 2. These are are more options in case you were, say, developing your own type of socket, which is very advanced. I'm not going to talk anything about that. The first type is a stream. And I mentioned a little bit about that. A stream is with full duplex, meaning that it can send back and forth. Sequential, meaning that the data being sent is ordered, and it will come out on the other end on that ordered, in that order. The stream in reality is a datagram, a series of datagrams, but they're so well connected together that the computer can interpret them as a literal stream. The datagrams are what they are, is like just a packet of information. And sometimes you hear about programs that send out packets and one at a time randomly, and it's not a contiguous stream of information. But for datagram sockets, they're full duplex, meaning that they're sent back and forth. They're non-sequential, which means that a piece of data might be sent here, a piece of data might be sent there, but overall, they don't have to be exactly straight in a line. And a lot of peer-to-peer network software uses this, where you might be downloading multiple different parts of the file at a time. It's going to be sending little data packets through, and then it ensures that once it's received that packet, it says, the client sends back an acknowledge sort of signal that says, I received this bit, send me the next one. And so datagrams are useful in that sort of situation where you're sending all sorts of pieces of data that may be received, maybe not, might be dropped, maybe not. So these are fairly robust systems can be built of this, but it must be done in a way where it has checks and balances. So data is sent and then data is checked to make sure that it's received, because it's not assured. This is like very, it's very difficult, more difficult to write a datagram program than to write a stream program, because you have to set in that system of checks and balances. Sequential packet is basically somewhere in between these two. It's not used as much, but it can be. Most of the time, if you need a sequence of data, you're going to send it as a stream. The main thing about this is that it can be done over long periods of time where you don't have a connection. Like, say you link up, and send a bit of data here, and then maybe you're going to unlink your system and walk around like your PDA or whatever. And so there might be pieces of data sent while your PDA is not online, but those are queued up and they wait. And then as soon as you connect in, the data is sent off and does its job. So you're not necessarily tied down to having a definite connection all times. But it does provide a connection for datagrams, and they have to be of a fixed size. There's just several little details about it, mostly implementation stuff. The raw packets are what is provided for programmers who want to make their own sort of new type of socket. And like I said, it's rarely done unless you feel like just inventing something. Yeah.
Remember a little while back when someone was saying that Windows XP was the first Microsoft operating system to implement raw sockets.
Oh yeah.
But Linux and Unix have them all along.
Right. Yeah. Windows sockets are much different than BSD, but mainly in naming. They try and follow it as close as possible. There's some that they obviously have to do implement so that they provide the data in the right sequence and things like that, but it's implemented differently on Windows. And the raw sockets are not necessarily huge that they have, but if you were to be like a developer and you're developing on Microsoft Windows, or you're writing, like say you're writing an application for Windows and you want to do your own sockets, you would need a raw socket to start with. That's really strange that they didn't provide it to begin with, because I think that all sockets would start off in a raw form. These are just these are implemented on top of raw sockets, so it just seems weird that they wouldn't give you access to that.
Well, yeah. See, the thing is that people were saying that was dangerous because of the hacking aspect. Because basically, when you have a raw socket, you're able to pretty much pump any data through that socket that you want. And
It's true.
I guess that's what they were concerned about, and this guy wrote up this long article.
Or you could maliciously, if a program's waiting for a stream of data or something like that, and you program your own socket, you could potentially mess with that and send something out of order or send something in a way that the stream was not anticipating, and it could cause a program to crash. Yeah, but normally sockets will only connect to others of the same type of protocol. So it should not be a condition that exists. The only way it could exist is if this raw socket was close enough to where the stream socket recognized it, but then somewhere like in the very middle or somewhere they did something malicious. I don't know. I personally have not ever delved into that, but I guess it's probably possible. You know, I mean, if you get down to it, I'm sure you could implement something that would do that. But hopefully not. Okay, here's a little bit about the two most popular domains on a Unix system, of course. Unix domains are used for local communication between processes, and they're bound to path names, which don't already exist in the system, usually in the temp directory. So I'll give you a quick example here with netstat. Right. So you can see here that in a temp directory, there is a socket here for the windowing system, X11. You can see that it is of type stream, and it is connected. And this is the inode, which is relating to the file system. And basically, common name of it would be /temp /.x11 Unix /xo. And there's also one for devlog. You can see I really don't have very many running processes on my computer, so I have very little. Like when Steve-O did a netstat earlier, it went off the page quite a bit because KDE has like many running processes, many of these locally communicating sockets. The other form is the one that you probably deal with most often and maybe even think about is the domain sockets, but you don't think about them as a socket, obviously not. You think about it just as an internet connection, and it's used for any sort of sending or receiving of data. They're used for remote connections, obviously, and they're bound to an IP address, which is in the form of dotted quads, or basically, if you were to get, you're going to have a number, say 0, 0, 0, 0, and the max, of course, is 255, 255, 255, and all IP addresses fall within this range for IP version 4. They've come out with version 6, which extends this with another two quads. And all computers that have an internet connection have an IP address, and they're uniquely addressable so that no two have the same. And so, like when you type in www.google, they're going to do a lookup and figure out. They're going to map www.google.com or just do google.com to an IP address. And there are name servers out there which do that for you. So when you type in an address into your web browser, I mean, this is repetitious for a lot of people, but sorry if it is, but it's going to go and do a lookup, and it's going to find the IP address for that, and it's going to then address that IP address with the socket. It'll connect in, and it can begin to transmit its information. Also, there are ports which can be transmitted on, and there's, of course, 65,000 different ports. The really common ones, of course, are port 80 for HTTP, which is your internet protocol, and then 81 for your file transfer, and 110, 25. They're like for mail. There's a lot of commonly used ports, but there's a lot of uncommonly used ports, as probably the net administrators here, admins probably know about. They probably get scanned on all of their ports regularly every day. Okay, and then there's different protocols, and obviously when you're communicating between two locations, you need to have a protocol. And we as humans, we use the English language, which obviously works sometimes and doesn't work other times, depending. But they're dependent on the type of socket, mainly because it's how they connect. Streaming sockets obviously are going to communicate differently than datagram sockets, because streaming sockets are a contiguous grouping of data, while datagram are going to be broken up over a period of time. So obviously you have to have different ways to ensure that data is reliably being transmitted. And of course, the really common one is TCP, which is Transfer Control Protocol, and it's used with streams. You use this every day to send data. It's right above the IP layer, and that's the Internet Protocol, which is closer to the hardware, obviously, than the TCP. Obviously, people here have some people here have taken some networking classes, and they linger on this. I actually have not taken that much networking, so I'm not really familiar with the details of this exactly. I went and looked it up. There's the DARPA, which is obviously a large group here in the U.S. and comes up with a lot of the codes. They in 1981 they made this official, and basically what they had to say about it is it provides a reliable system to transfer data, control flow, multiplex, connect via handshakes, give precedence, and security. So it's a set of communications which occur between the computers on a very low level before the data is even sent, to ensure that the data is being transmitted. This is where you have packets, and those packets are being wrapped with headers, and those headers are being transmitted out. That obviously happens on the kernel level and on hardware level as well. So that's pretty low level, but a lot of interest there because it's the mechanism which allows information to be transmitted. For datagram, we have UDP, which is User Datagram Protocol, and basically it's very, very, very simply put out by DARPA. It's actually like less than a page, and all it says is that it's a protocol where delivery and duplication isn't guaranteed, and there's a few other specifics on how that is, but it makes sense being that it's datagram. If you send out a piece of data and your receiving client is not even connected to the internet, you can't guarantee that client received it. So that piece of information is retransmitted continuously, or maybe it'll wait until it gets a signal back from the client saying I connected, and then retransmit. So it's a more unreliable system, but it's really effective in certain circumstances where you don't need a continuous, or you can't supply a continuous connection. I think I have a little slide here about protocol relationships. Here, there's different levels, obviously. Here's the hardware level, the physical level. This is kind of give you like a hierarchy of what we're talking about here. There's the local network protocol level, which is like your routers, or you have that set up. I'm not too familiar with this, so I didn't do my research in this area very much. The networking protocol, which is the IP level, which is what is going to receive the different protocols coming from programs, is able to then transmit to this level and then to the hardware level, which will transmit. And each one of these is an exclusive, exclusively different from the level above it, meaning that this has a defined way of communicating with this level, and this level has a defined way of communicating with this level, and so on and so forth, coming back. And if there's an error received on one level, it's communicated up through, and it's worked out many years ago, back like in the 70s. Obviously when most of computer science was evolving. On the host level, what your computer, your kernel is going to deal with is going to be, the TCP, and RTP is real-time protocol for sending like voice and video. It's not really used very much anymore, but there's several other protocols. Most commonly, of course, is TCP and UDP. And then application level at the top here, where, file transfer, telnet, your web browser, your email client, all those reside on that level. Okay, and I mentioned earlier that sockets have options that give you minor adjustments to tweak how they work. You can, in C, and in most languages try and keep a similar way of doing things. They don't want to do things too differently. You can give the socket options, and you can set socket options. These are functions, or basically little tools that allow you to do that. And you have options here that you can actually do. Like, so you can make a socket be able to reuse its address, meaning that once the address has been used and the connection has been completed, it'll be dropped out, and the socket is closed. Normally, you cannot reuse that address for a given amount of time unless you select this option. There's a keep alive, which means that if this is selected, that you can actually, it'll keep a connection alive up to 2 hours trying to communicate. Broadcast will be, allows messages to be broadcasted. There's going to be messages that can be broadcasted out like across other sockets and things like that. It gets very touchy and difficult on that level. You can set the size and of your sending and receiving buffers. So you can say how much of this socket is kept in memory before it can be used. So, obviously if you pile up a huge amount of information coming in and you're not reading that information out, you might want to increase the size of your buffer or decrease it. And you can set the type of, you can get the type of socket only. You can't set this, but in certain cases, like in using a program, you want to know what type of sockets you're using or what you're connecting to. So these are just little tools used by programmers mainly, but they do exist. And I think this might be it. Let me see. Okay, client server. Okay. In a little bit, I'll show you a few little trivial C programs that I wrote to implement this. It's pretty basic, but the client server model, the server is going to create a socket, and like I said, it's very primal. Like when it creates it, it's not well defined. There's no addressing. There's really no information there besides like an integer. It binds that socket to an address. In the case of a Unix domain socket, it'll bind it to a path name, meaning that it'll give it an actual location in the file system. For an IP address, it of course gives it the dotted quads and a port number that it can connect on. Then it begins to listen, and there's actually a function called listen. And once your socket is listening, it can accept new connections coming in. So a server will make a socket, give it an address that it'll listen to, and then it'll just start listening, waiting for incoming connections. When a new connection comes in, it accepts it and it forms a new socket. So if I can kind of draw it around the board really quickly, like I'll try and make this as clear as possible. You have a server here, right? And it makes a socket. I'll draw little pictures because it's very easy to visualize. So this is your server sitting off somewhere else, and it's listening, and it has a socket ready to connect. And then here's your browser, your scroll bar, your Google. So then this will connect in, and it'll say I want a connection. And as soon as it sees this connection, it opens up another socket here at the server. Right? And what this does is it reroutes this connection into this socket. So this socket here may be on port 80. And it's waiting for an internet protocol coming in, right? This socket over here might be on port 3048 or 47 or something like that. Some crazy number out here. So you connect in and it spawns off a new socket, and then on this the communication can occur. But you also notice that port 80 is still available. So another client, like say Steve-O over here, wants to connect in with his client. He likes Google too. Everyone does. And so he connects in, and the server says, okay, you need a socket now. And so it'll make a new one. And connect in. So the system allows for one server to handle multiple incoming connections. And of course, the server has to spawn off these children. And once it does that, the children know their job, because every process is given a bit of code to execute. And it'll execute the code, and it'll deliver a web page over here to the client software. That's sort of a simplified version of, actually, it's pretty much basically it. So to reiterate what I drew in words, the server creates a socket, it binds the socket to an address, and it listens for incoming connections. It accepts the connections, forming a new socket. It possibly forks off a new process to handle the connection, and then it sends and receives data until it's done, and then it closes the socket out. So that would be that part. So once it's done, these sockets close. You turn off your Apache. You stop the process, and everything's good. So.
Is there a way that you can physically, or not physically, but is there a way that you can tell it bind permanently to that port 80 socket?
Yeah, exactly.
And thus it would, in essence, just launch like a denial of service, wouldn't it, or something? Make it so that other.
Yeah, you could bind a socket there that does absolutely nothing. And so when they come to connect in, it'll connect in and just drop it, and then re-listen and do nothing. So when they come in, it would just drop it, and it's basically the bit bucket, like what you're talking about. Like they come in, try and connect, it would just drop it back and re-listen on that same address. So you could do that. You could do that.
But the server would actually drop it and then reroute to that secondary.
Oh, it does that automatically.
Right, but is there a way to force it not to drop and to reroute to that secondary?
You're talking about DOS attack, right?
Well, not necessarily. Like, okay, you make that initial socket connection, port 80.
Okay.
Then the server will drop it and reroute or redirect it to the secondary
Well,
port, the 30,000.
it creates a new socket when it accepts. The accept command automatically creates a new socket, and that's just the way that the BSD sockets were created, and that's the way that you interface with BSD sockets. Of course, you could implement that, but it would be pretty massive to do. You'd have to kind of rewrite a new application, like API, application programming interface. But I know what you're saying. Like if it just connected in and then did nothing and just held it, kept connected. Is that what you mean?
Right.
Yeah.
You didn't allow it to spawn that secondary socket.
Right. You could do that where you only accepted one internet connection at a time. And in fact, I actually no. There is a very easy way to do that. It's right here. It's right here. You don't fork off a new process. What it would do is your server would make a socket listening on port 80, and then you have your client, whatever it is, it would connect in, and then it would get rerouted to a new socket, but this socket dies. You see what I'm saying?
Yeah.
And then that is connected. So as long as this is connected, it would be listening. But then again, you're not listening on port 80 anymore.
You could tell Apache to just have one instance of Apache going at any given time, and that would take care of that problem that you're talking about.
Right. But I think Apache might still fork off processes. I think it's set up to do that.
Even though you say
It
allowing.
might not be threaded, but it would still. I don't know. I've never messed with that on that level. But on the programming level, I know it's for certain you can program it not to fork off a new process. But then again, like you're not willing to accept any more incoming connections at port 80. So
They'll probably just disallow the socket connection in the first place.
yeah, you're better off if you're doing a DOS just to shut it down.
I was looking at it from a security standpoint.
Yeah.
So that, I mean, is it possible?
Yeah, you could not bring down your server, but you'd have to rewrite your server code that it's running on, which is like most people just want to run Apache because writing on web server does take some time, and security concerns do matter.
There's also a program called Netcat. Have you ever messed with that?
Yeah, NetSaint, isn't it?
No, Netcat.
Yeah.
It binds to an address. Like, say you're getting weird traffic that keeps coming to this port.
Yeah. And
You
you can
open
tell
up this
what's
port
coming
and
in.
you just suck in whatever they're sending to you, and you keep it in a file. It's like, okay, and it dumps it to a file. So you can check it out later. It's pretty cool.
I should check that out. Actually, I probably could use something like that for this, like what I'm about to show you. Of course, in this model, the client is simpler. Obviously, I mentioned it's not symmetrical like their jobs. Its job is to create a socket, connect to an address. There is a function called connect, and in the BSD style of sockets, and it binds to an address automatically, and it sends and receives the data to the server and then closes. So this is, I think, coming back to your question, I think what you're asking is higher level than this. This is relatively low level. So this will accept a connection in, and it'll fork off a new process to handle that communication. But if you drop that communication, or whether you keep that communication, it's up to you. So, and I believe that's it for this part of the presentation. Okay. So I prepared a few small. A few programs here that I'll show you. That's in the FOSUG server. And it's probably a little hard to see. Actually, probably really hard to see. Let me boost out the font on here. Language environment. What is it? Set font. Let me just see how big I can get this. There we go. Can you kind of see that? Okay. It's going to probably run off the page here, but anyway, so in C you include these libraries, and I have a standard input library, a string library, types. This is the big one here with socket in it. And I included this library here, un.h, which is for the local Unix sockets. And if you ever really get interested in some of this stuff, just in case, as a side note, you can type in man un.h, and you have a manual page for the header, and it tells what's in that library. Like just like you would type in manual for a function or a program that you're going to use, you can also do manual pages for your actual for actually most of the C programming functions and libraries. So anyways, that's a side note. And we have a few other things. So I made a few global constants here underneath the see if I can get this so I can see it well. Okay, these are some global constants. I made a header, and it's just a string hello. It's like really simple. It's like such a simple program. And I made a body of code which I'll send called welcome to FOSUG. Okay, and because this is being done on a Unix domain, this is going to involve a file, because Unix domain sockets address through a file, like I showed you, those temporary files. So my file name string is going to be temp FOSUG, and it's our core function here. Anyways, our function, this is not used actually, but I left it in there anyways. So here's our actual program. I'm going to create a socket. It's pretty basic. You have a function called socket, and you tell it that I want it to be in the address family Unix, and I want it to be a socket stream. This is the domain, and this is the type, and I'm going to use the default protocol. And then we do some error checking just to make sure that we create the socket okay. So that's step one. We created the socket. See, like what I said, the socket is just, at this point, the socket is just an integer. I made an integer called socket, and at this point, it's just a number, like 3. Really simple. Okay, now we bind it. This gets a little, I'll try and separate this out because it gets a bit messy. Okay, so we're going to give a socket a name, and you have to make this special structure that holds a socket address, and I just called it address. And inside of this structure, there's 2 parts. One is the family, which is AF Unix, because that's the type that we're dealing with, and the path name. And the path name is FOSUG. So this is the part right here where I stick those into there. I say assign the value AF Unix into here, so it puts it into this part of it, and assign the file name FOSUG, and I stick it in there. That's really low level, basic. It's some C programming. If you're in other languages, you don't even have to do that stuff. It's nice. But here's where the actual call happens, and I bind the socket, which is at this point is just a number, to the address that I put inside that structure. And then you have to give it the length of the address, which is the length of the path name plus a few other bits. C is so low level. It's pretty basic. Sorry if this is boring, but it's a bit into the world of a programmer, if anybody's interested in that. And then I test to make sure that went okay. And then now that I've made the socket and I've bound it to an address, then I'm going to listen. And I'm going to listen for the socket, and I'm only going to listen for one socket at a time. So you start listening on socket, accept one connection only. You can set this to like 5 or 10, and it's called a backlog. So you could have like 10 sockets trying to connect in at once, but if the 11th socket tried to connect in, it would drop them, which might be something along the lines of what you're asking about as well. So I've set this up to only accept one at a time. So if the second socket tries to connect in, it gets booted out. And I do another error checking to make sure that the listen went okay. Now that it's listening, I create a new socket, just like I did before. So that's all copy and pasted, basically. And then I do an accept call. And the accept call is going to actually sit there and wait. In this case, it will sit there and wait. It's called blocking. And it means that if you have a blocking connection, it's going to wait, and it's going to wait, and it's going to wait until it actually gets something that connects into it. You can do a non-blocking call too. It's slightly different. You have to do sort of like a socket option. You have to do a function call, and it'll do non-blocking, which means that if you do an accept, it'll be instantaneous. If there's nobody there to connect to, it'll keep going. And so sometimes you could loop in there and just keep waiting. But there's better ways to do that. Since this is so easy and very simple, I'm just going to do the accept call, and it's going to wait. So when I actually run the program, it'll do all of this stuff up here, and it'll get to this point, and it'll just sit there, and you'll just see the cursor like waiting. It'll just be blinking, waiting for an incoming connection. And then we make sure that we do a little bit of error checking as well. And if at this point we actually have an open socket, so if an error occurs, we have to close it, and we have to remove. This is a really cheap way to remove a file. You can execute shell commands inside of C. Anyway, so that's the part where it's going to sit and wait for the incoming connections. And once we get an incoming connection and everything's okay, we can start transferring our data. And here's the input. And I make a buffer, a character buffer, called input, and it's going to be this big. The length of our header, which is the word hello, +1. And that's because of a C reason, nothing important. And to read and write, you just use read and write. The same thing you would use to read and write from a file. And so that's the reading section, so it'll read it in, and then it'll compare it to make sure that that the input was actually the word hello. It'll make sure. So it does a string compare to make sure that the word input is actually the word hello. Because if it doesn't get the right word hello as an input, it's sort of like a header. If like it gets the word Steve-O, then obviously it's gonna say this is an incorrect program accessing me. Just like if you were to connect into an HTML server, like I'll show you in a little bit, if you don't send the right HTML header, you don't get anything back. But if you send the correct one, you get a whole web page back. So this is the header that's being sent, and then if the header is okay, then we get to write. We issue a write command, and I'm going to write to the new socket that I created, and I'm going to write to it the body, and the body is welcome to FOSUG. Okay, and after I'm done with that, I'm done with my error checking. Then I can clean it up by closing out I can close out my original socket, and I can close out my new socket. I could have closed the original socket out way above, but I was lazy. And then I remove the file that it creates, because remember, Unix domain sockets create a file, and I'll show you that file that it creates. So now that we have that done, I'll actually compile it real quick. So we can go here to FOSUG folder and gcc server.c. Actually, I'll rename it to server. Okay. So let's run it. Server. And you see that it's doing nothing at all. It just sits there. So the cursor is just stalled, right? Well, oops, I should split it the other way. Just a second. Okay, but if we go and look in the temp file, or the temp folder, we can see right here, it may be a bit hard to see, but there's this file FOSUG, right? Oh, actually, there's a clearer way to show this. Excuse me. I'll kill that. And I'll remove that. Okay. So now, if I go over here and I list what I have, there's no FOSUG here in my temp directory. And to show you that it would be faster to show you it appearing if I had a graphical interface of some sort, but I don't. So imagine, if you will, that FOSUG just popped up right here. So here I listed it. It wasn't there. I ran my server program, and it created FOSUG, and I listed it again, and FOSUG pops up. So I actually have FOSUG. I actually have a Unix domain socket just waiting. But if you do a netstat, let me clear it first. If you do a netstat, you notice it's not listed because it's not connected yet. It's just waiting. It hasn't actually made a connection. It's not even a full socket because it's unconnected. It's half of what you need.
What about if you did it a netstat -L?
Okay.
Check for a list for processes that we're listening.
Yeah, right here.
On
Yeah. Unix 2, it's a stream listening, and it's temp FOSUG. Yeah, way to go. I should have looked. I underestimated the power of netstat. Okay.
I want to go back to, okay, back to Emacs. All right. Now I'll show you a little bit of the client program. I don't want to spend too much time on it, but hopefully this will kind of show you what the life of the program is. Client, let's see. Okay, here's the client. So the client is going to do the opposite of what the server is going to do. It's going to connect into the server, it's going to send the words hello, and then it's going to receive a bit of information back and then print it out, whatever that information is. It should be welcome to FOSUG. Okay, so it's pretty much the same. I create the socket, I copy in the information, say that it's a Unix socket, and that it's going to go to the file temp FOSUG. It needs to address the same location as the other one. And then here's where it actually differs. I do a connect, and I connect to the socket at this address and the size of the address. Not that that really matters. It's mainly, like I said, a C thing. And then once I'm ready, I do my data transmission. And my header, of course, is the word hello, and I write that out to the socket. And then I do an error check to make sure that the write was okay. And then for the input, I make a buffer, or make an area of RAM of this size, and then I do a read from the socket and the length of what I'm expecting, which is probably hello, welcome to FOSUG, that's what it is, welcome to FOSUG. And then I make sure that it's okay, and then I compare at the end, and if it is, welcome, if these two strings are equal, the one that I read in and the one that I was expecting, then I print out my result. Fairly simple, but it looks complex, you know, because of all the code. All right. So let's actually run this thing. Okay. GCC, which is the compiler, client.c, and then the output will be client. And when I actually hit enter, it's going to do the communication. So this will write hello to that file that I showed you that appeared, and this